All right, for the sake of time, since I think everybody who's going to show up has shown up already. Hi, I'm Riley. I'm a master's student. This is my 6th year at Cal Poly. For my master's thesis, I've been working on formally verifying 2 risk cores, one from 233 that's single cycle, so it takes a whole cycle to execute one instruction, and the pipeline version from 333. With that knowledge and experience, sort of getting better at using those sorts of tools and understanding the theory behind them, I've been trying to create some lecture material related to formal verification for like the 2033, whatever they're going to call the new class, that's specifically related to HDL design and verification. To kind of give you some background on what formal verification is, because it's a pretty amorphous concept, I think the best way to describe it is in terms of what everybody else already knows, which is functional verification. That's kind of like the standard way that you unit test something. You have some device you want to test, some input that you send through the device, and you check the output to make sure it matches what your expectations are. And the more and more inputs you test, the more certain you are that the device is correct. Formal verification kind of turns that on its head by, instead of checking inputs and outputs, you're now trying to sort of prove specific claims about the internal implementation of the device using some form of mathematical reasoning. And that's a pretty wide term, but there's so many different topics it's hard to really kind of pin down a specific one without kind of narrowing it too much. But generally speaking, functional verification is simpler to implement and run, but you only get sort of a probability that your thing is correct. There's some sort of uncertainty that you could have a bug in your design just because it's impossible to test every possible input. The kind of easiest way to conceptualize this is functional testing. Think of comparing like 2 equations. The functional testing approach to that to prove that those 2 equations are equal would just be to give it a bunch of inputs, check if they match, and over time you can be more and more certain that the 2 equations you have are the exact same thing. Whereas formal verification requires you have some kind of deeper knowledge behind how the equations are structured, how like the operations go. But instead of having some probability of certainty that these are the same, you can be absolutely certain that those 2 equations are the exact same. So some topics that you're going to see a lot of when you look into formal verification, there's kind of 4 main ones that apply to ASIC design: theorem proving, model checking, equivalence checking, and symbolic trajectory evaluation. Theorem proving is like pen and paper proofs where you, like, mathematician sits down, comes up with some theorem, writes it, tries to prove it. Model checking, it puts a little bit of the work onto a machine where you design some implementation, you come up with a set of assertions that implementation should behave with, or like should a set of assertions that implementation should not break, and then a tool checks to make sure those always hold for all states. Equivalence checking compares 2 designs, and symbolic trajectory evaluation is just kind of like a fancier form of model checking that uses a different tool that we aren't going to go over in this lecture. The main one that you're going to run into most of the time when you're dealing with ASIC verification is going to be model checking. So that's what we're going to focus on today and kind of give you some of the background on how these tools work. So, as I kind of mentioned, model checking, you start out with some specification for your device and you translate that, like the design process is you take your specification and you create an implementation of it in RTL. To do model checking, you also create some sort of behavioral assertions that describe how the RTL should behave. So something like this input or this output should always be this way if this input is this way. And then you feed those 2 things into a model checking tool. The model checker checks for all possible states, do those assertions, hold for that implementation. If they do, it passes. If they don't, it'll fail, and it will give you sort of the sequence of inputs and states that cause that assertion to fail. It'll give you a counterexample that you can then go and debug later, essentially. I think before we even get into how these tools work, though, it's important that we understand what it means for something to be proven correct, because there's a lot of sort of, like I would say, useless things that you can prove about a system that don't actually give you any level of certainty about whether or not it works. There's a cool paper that I read, it's cited in the references, but they sort of boiled down all sorts of correctness proofs down to 2 properties that you need to prove, which are safety and liveness. Safety is trying to show that some bad behavior P never happens. So it would be something like, if my CPU interrupts, the instruction that's interrupted doesn't update the registers. You don't want some bad behavior that shouldn't happen to happen. And so you define a set of properties that check for those bad behaviors. The liveness properties are kind of the opposite. You want to show that some good behavior either eventually happens or always eventually happens. The distinction there's kind of a little bit fuzzy, but saying something eventually happens, it could happen once and then never happen again. Where always eventually happens means from wherever I am at any point, I should be able to get to that eventually. Which is, if anybody's confused on that, you can, because that is a little bit of a weird term, but some cases, like you could think of like a CPU at any point should always be able to execute an instruction. That's an example of liveness. It should never reach a deadlock state where it halts. Another one's like an arbiter that has 2 ports that it's controlling. It should eventually service either port. It shouldn't completely freeze out one port and only feed the other. So those are sorts of liveness properties that you need to prove to have your system be considered correct. You can think of, kind of conceptualize these as kind of like at an intersection with a stoplight. If all the lights are red, no cars move, to track like no one's ever going to get into a crash, but nothing ever happens. That sort of setup is safe. Like it's never going to violate any safety checks because a car can never crash when every light is red, but nothing happens, so it's not really that useful. A device or like a set of lights that are always green where every car can go, it's live, so things will happen, but you're very likely going to have a car crash, something's going to break. So if a device always does something, even if it's wrong, it'll pass the liveness checks. So you need this kind of balance between safety checks and liveness checks to prove that something is correct. Otherwise, you can't really say much about your design. So now that we have sort of an idea of model checking, of how we can prove that something is correct, and we have a sort of some set of properties that we know that we need to prove, how can we do it? Like, what's the solution that allows us to do this automatically? The standard way nowadays to do this is to translate model checking, like the trying to prove something about a system, into a satisfiability problem. So for those who haven't kind of run into satisfiability, it's really just you have one massive Boolean equation with a bunch of variables, and the goal is to find if there's some assignment of true or false to those variables that makes the whole equation true. If there is an assignment that exists, a tool that can solve a SAT problem will return the assignment and then will tell you that it's satisfiable. If there is no assignment, it'll say that the equation is unsatisfiable. And we can rephrase our model checking problem in terms of SAT and use a SAT solver to solve the model checking problem for us. So that kind of looks like this. So if I want to create something that can model check my device, I can input a model, some number of cycles I want to check, and some properties. I can feed it into the model checker algorithm. And what it does is essentially it takes your model checking problem and translates it into a SAT equation where if the equation is satisfiable, your system will break eventually in those end cycles. And if it isn't satisfiable, then you pass your checks. So the SAT solver will run, and then if it finds some satisfying assignment, the tool will turn that into a counterexample that you can use to debug your state or to debug your system. And if there is no counterexample, it'll say your system passed checks. Everybody good so far? Okay. This is what we call bounded model checking. The bounded part there is important because if you notice, there is this new sort of number of steps n. That's essentially saying that what a bounded model check does is from the start state, it checks outward like some number of steps, whatever you provided, and proves that the model meets all those properties for just those steps. You need to have that sort of step limit because otherwise there wouldn't be the equation would just be infinitely large, so you need some way to say like, I'm only checking up to this amount of steps, because the more steps you check, the bigger your SAT equation. But this allows you at least to get sort of the first step, which is to prove that a system behaves properly for some number of cycles. Some people who are more experienced with this might notice that we're using SAT. That's a provably difficult problem. In the general case, it's as you increase the size of your formula, it's going to get exponentially harder to solve. But luckily for us, hardware generally is going to have some sort of like logical pattern to it. You're going to have some way to, sorry, it's a lot of words I did. But it's going to have some sort of like logical pattern that you can use to cut through the work. So like the modern solver tools are able to find these patterns, recognize that this chunk of, whenever I see this sort of set of variables in this structure, that's always going to be true, but that's always going to be false. It uses that to cut away a lot of work for us. Some of the more modern solver tools, that things like bootlector and Z3 that we use, also support things like what are called SMT, which just instead of just looking at Boolean equations, it generalizes it to things that are like on the real numbers, data structures, stuff like that, which would take a lot longer on older tools. So there's been a lot of work that's gone into these tools that makes them still perform relatively well for small or medium-sized designs. And so even though the problem itself is hard, in general, the problem is still manageable for hardware verification, so we can still use SAT. And that's where symbiosis comes in. That symbiosis is an implementation of kind of exactly what I mentioned. It takes a model checking problem that we write out in Verilog, which is going to have some implementation, some assertions, and it translates that using Yosis, that kind of Yosis front end. It parses the Verilog into what's called SMTlib. SMTlib is just like a SAT problem format file that you can then feed over to a SAT solver. It'll solve the problem for you, hand it back to Symbiosis, which can then either construct a waveform file if there was a counterexample, and otherwise it just tells you that you passed your checks. So it's just kind of a system that allows you to do SAT-based model checking with Verilog. This one isn't as important. It was just more just to show you how you can run the tool. You define some set of like what jobs you want to be able to run, how many cycles you want to run the job for, what engines you have, and what files you want to run the task on. And then you can invoke SDY to run whatever task you're interested in on that file. So now that we're actually getting to the interesting part, being able to run model checks on Verilog, Symbiosis gives us two ways to interact with the solver, which is through assume statements and assert statements. Asserts are kind of like you'd expect from like unit testing if you've ever used like things that check if you like the functions from unit testing where you like check to make sure that the output is correct. It's the same kind of idea where it defines what things are illegal by saying if the solver encounters an assert that isn't true, then the BMC is failed. So it's like you assert some property that should always be true. And then if it's not true, the solver will tell you that it's not and give you an example of how it found a way to make that assertion not true. Assume is kind of the other side where you assume states that should never happen and don't make any sense to test. So usually you're going to assume like the driver, the master or driver to your circuit behaves in some certain way. It implements this protocol, so it's not like sending you random inputs. It kind of constrains how the solver can interact with you, just so the solver can't just do some really random stuff and break your thing, essentially. To kind of visualize this, what a BMC looks like is you'd start at your initial state, and then the solver starts and walks out from that initial state and tries to find a way to get it into that region that's illegal or invalid. And if it can find a way to do that in the number of cycles you gave it, it creates a waveform file for you and hands you the steps it took to get to that illegal state. And as I kind of mentioned, assert increases that range of illegal and valid states, making it more clear what's good and what's bad. And assume constricts the amount of total possible states so that you can't, it can't create weird, invalid conditions that you should never encounter when you're like running an actual simulation. Everybody good so far? Okay. Some interesting things that symbiosis also provides along with those assume and assert functions. There's the pass function, and that lets you interact with states that have happened in the past. So if I want to say, show that a signal is stable over some number of cycles, or just have some precondition that leads to something happening at a later state, I can look at, or I can create these kind of pass function calls that give me the result of that signal one cycle ago. So like for example, if you guys have any experience with ASIC, one of the common things that you want to check is if my circuit outputs something valid and the reader doesn't take anything this cycle, it should still be valid next cycle. And so that's what this check is doing. It's just checking to make sure if I have a valid response and somebody doesn't try to read from it this cycle, then the next cycle it should still be valid and the data signal should be stable. One kind of important caveat and one foot gun that I ran into a lot when I was working with pass is you have to precondition every pass with this little something. You can name it whatever you want, it's just a variable, but something that makes sure that your the pass functions are valid. Because what will happen is pass is essentially just checking some number of cycles from where you are. And so if, let's say you're in cycle 1 and you call and you encounter a pass call, the pass doesn't exist yet. And so the solver is just free to choose whatever value it wants to, and it'll choose the one that breaks your design because it can. So you always have to make sure to add a precondition that guarantees the pass exists before you use the pass functions. Yes?
Is there a future?
What? There's not. No, that's good. That's all the SVA fancy tools. Yeah, you have to go because all this, the paths are really simple. It's really just like when it's parsing it, it just turns it into its own, like a separate register that captures the value one cycle ago. So they just tried to make it as simple as possible. But yeah, they don't have any kind of future stuff, which is unfortunate. It does make some of the other stuff harder, but gotta pay money. The other cool feature that symbiosis gives you is free variables or arbitrary values, whatever you want to call them, that are essentially a way that you can tag some variable with any const or any seek. These two things essentially just tell the solver, hey, pick whatever, either a constant value for the whole simulation or a sequence of values changing every clock cycle for that variable. And that lets you do some interesting things. So for example, let's say I have a FIFO that I'm trying to check, and I want to prove that every transaction that I write to it, when I read that transaction, it doesn't get corrupted. What you can do is you could say, all right, pick an arbitrary constant value to watch, or like an arbitrary constant index value to watch, and then on that index, when I write to the FIFO, I'll track what data I wrote, and on that, the read index, I can then compare those two. So it's essentially like I can pick an arbitrary transaction during the formal check and make sure that the data going in is the data going out. And that's a pretty common check that you see a lot of the time is there's some, like using some way of, or using these sort of unconstrained values to pick specific arbitrary values instead of having to write tons of checks that check every cycle. You can just write one check using any const or any sequence. As I mentioned, so that's the last feature we need to look at for BMC. But as I mentioned, it only provides certainty for some number of cycles. If we actually want to do unbounded proofs, we have to go one step further and prove them inductively. So for those who have taken 248 or any sort of like discrete math classes, to kind of give you some background to how induction works, you have something you want to prove that has some sort of like natural number or some sort of sequential thing. You start by proving the base case, in this case showing that P of 0 is true, and then the inductive step is assuming I start at a place that's true, if I take one step forward, I should also be in a valid state. And so that lets you, inductively, that allows you to kind of prove a chain of things. So now that I've proven the base case and I've proven every step I take leads to a valid state, I can just create a chain of everything being true going on forever. And so I've proven that P holds forever. K induction uses that same reasoning for model checking to create our unbounded proofs. The main difference is that instead of just a single case, we use a bounded model check to prove that the system begins in a valid state for some number of cycles. And then the inductive step, instead of just assuming I'm starting in one state and checking the next state, it's allowed to assume that I have a sequence of end states that's as long as my bounded model check. And then it takes one step further and sees if the next state is true. So what this kind of looks like is, let's say I'm at the start state at n equals 0 for my bounded model check. I'll start there, I'll take one step, assert things are true, and I keep on doing that until I build that kind of circle of truth in that bounded model check, giving me my base case. Once I've done that, the inductive step just picks a random arbitrary sequence of states that my assertions say are valid, and then it tries to go one step further and see whether or not the n+1 state is valid. If both of those things pass, then you've proven your system works forever, essentially. You've done an unbounded proof, and you can be certain that at least your RTL is correct, as long as your assertions are good enough. The one thing, and probably the biggest kind of pain in your side you're going to run into with induction is that a lot of the time there are states that aren't valid, but aren't explicitly marked as illegal by your assertion. So it's just something that you didn't think of, maybe two counters going out of sync, or something that would never happen if you started from the reset state, but you didn't explicitly label it as illegal. So the induction check allows it to just drop it outside of the bounds of valid states, and then it'll walk its way into an illegal state. So you have to be good about sort of making sure you cover every possible, either assume away all the unreachable states or strengthen your assertions such that there isn't this kind of gray area which isn't necessarily valid but isn't explicitly marked invalid, or else you're going to have a really tough time, and it's going to be very difficult to prove things. With that though, even after, kind of as I mentioned, even after you pass BMC, you're very likely going to fail induction, but that really doesn't mean that your device is wrong or any of your assertions are wrong. A lot of the times it just means you need either stronger assumptions or stricter assertions that show or that cause those kind of invalid but not explicitly illegal states, or it makes it impossible to reach those invalid but not explicitly illegal states. There's also some different solvers called like ABC and Eiger that use a different method. It's like and/or inverter trees instead of induction to do proofs. That can sometimes deal with that for you, but they also take way longer. Like a proof that took like a few seconds inductively took like an hour with that. So I don't know. Your mileage may vary with those. But if all else fails, you could also just, it could just be that your base case is insufficient. It has to build that long sequence of states. So if you, sometimes it may just be that you have to increase the amount of states that your bounded model check runs. And if your base case is big enough, eventually, sometimes that'll cause the induction to surpass. So those are a few things that can help with induction. The last two topics I have covered today, or the last topic I have, is cover properties, which are just kind of a useful tool that you have in your tool belt when you're trying to debug things. Another common issue that a lot of people run into is you want to prove, or not even just prove, but just see that something is reachable. So like, for example, maybe I design a FIFO, and I want to make sure that it can be completely emptied or filled. And that, problems with that can happen where like I write a bugged implementation, like you can run into problems where you write bug or you have bugged code, or if your assumptions are too strict, it may cause some states to be unreachable. And so cover properties let you quickly see if a state is reachable. So you can either say like, oh, I just overdid my assumptions too much, I need to back off a little bit, or it can help you detect a bug. Cover properties are essentially the exact opposite of assertions, where assertions, the goal of the SAT solver when it's doing a model check is to find a way to make your assertions false and then show you how it made your assertions false. The point of a cover check is the SAT solver is trying to find a way to make the cover statement true, and then it will return a waveform that shows you how it made the cover statement true. Okay. But yeah, So it's just a way of making sure that some behavior happens, and it gives you a way to see how that behavior happens. With that, I guess quick little recap quiz. Does anybody remember what safety properties prove?
That something doesn't happen?
Yeah, that a bad thing can never happen. For liveness, the other side, what does that prove?
It does happen.
Something, what kind of thing? Something good always happens, or eventually happens. Kind of the two sides of it. For comparing BMC and induction, which one do you think is the right one? Hands for A. B. What? Do you want me to read it? I don't know. I'm slow. Yeah, that's fair enough. Anybody have any ideas?
Z.
Yeah. Yes. BMC checks the property holds for K steps, and induction goes one further step. And then for assert, assume, and cover, which function defines the illegal states and will make the check fail if it can find a way to make the stuff inside the parentheses false.
Asserts.
Yeah, assert. The one that restricts the states that can be covered, so you can't make, it tells the solver that this thing can never be false. Assume, yeah. And the last one, pretty clear, just based on the trend here, but something that defines a state that should be reachable, and if it finds a way to make it true, then the check passes. That's a cover. Okay. Okay, so these are more interesting. Other than that, so the next thing I have is, if you guys have the time, I have a lab that's going through and teaching you how to do those kind of safety and liveness assertions on really simple ASIC stream FIFO. They're just something that takes in data and outputs data in order. Yeah, sorry, I thought there was someone raised their hand. I have the link is in CARC, but also on the slide you can pull it, and it runs. It works with the CARC Docker container. So if you guys already have that installed, you should have the tools to be able to run it right now. The main three things you're going to be looking at are just trying to show why a FIFO that can overfill or underfill is broken, why one that corrupts data is broken, and why one that does absolutely nothing is broken. And if you can do all that, I have some extra checks in there that I added for you so you guys don't have to go through the pain yourself to do that. Make it strong enough so that your earlier check should be able to do an unbounded proof. And then you can inductively prove that the FIFO will always work. With that, there's kind of the references from there. Well, that's it.